So today we're looking at AS Physics Unit 2 from CCEA in 2023. Okay then, let's get going. Question 1A. Water waves are classified as transverse waves. Part I. State another example of a transverse wave. Okay, so all electromagnetics are transverse, so that would be an easy one. Someone wiggling a rope would be transverse waves. But yeah, I would just put an electromagnetic down. State an example of a longitudinal wave, and our go-to for that is always sound. Part 3 then, with reference to the motion of the particles of the medium through which the wave passes, what distinguishes a transverse wave from a longitudinal wave? Okay, so when you're answering these questions, you've always got particle vibration direction, wave propagation direction, and an angle between them. So in transverse waves, we've got vibrations that are perpendicular to the wave direction, and in longitudinal, we have vibrations that are parallel to the wave direction. Something along those lines. So part B then. A graph of displacement against time for a water wave is shown in figure 1.1. On figure 1.1, label the amplitude of the wave. So we remember the definition of the amplitude is the maximum displacement from the undisturbed position. So we can see that central axis is the undisturbed position. Amplitude will be measured from that location. So we're also supposed to label it A, because they've called it amplitude A. Part 2 then, use the graph in figure 1.1 to determine an accurate value for the period of the wave, and they have said accurate value. So let's bring that graph back. Okay, so you can see we start at a peak here, then that's 1 wave, 2 waves, and 3 waves by the time we get to 2 seconds. So that's quite good. We've got 1, 2, 3 waves and a time of 2 seconds. So if you divide the total time by the total number of waves, you're going to get how long each wave took. So we've got total seconds of 2, total waves of 3, giving us a period of 0.67 seconds. And I've just marked how many waves we're using on the diagram to help us. So 1 wave, 2 waves, 3 waves. By the time we hit 2 seconds, that's where our numbers come from. Okay then, part 3. Oh, that wouldn't move. Okay, part 3. The wave is travelling at a speed of 3.50 meters per second. Calculate the wavelength of the wave. Okay, so we've got a period and we've got the idea of a speed here. So we can get a wavelength by converting that period into a frequency and then using V equals F lambda. Or we could just remember that F is the same as 1 over T. So 1 over T times lambda should give us the same result. So effectively then lambda over T equals V. And therefore V times the period T should equal lambda. And that gives us a wavelength of 2.3 meters. Part 4 then. On figure 1.1, draw a wave of the same amplitude but 90 degrees out of phase with the wave shown. So we need a graph back for this. Okay, so 90 degrees out of phase is like a quarter of a wave. We think of 90 as being a quarter of a circle. So a quarter of a wave is to here. So that's where we're going to start, up there. And then by the time we reach the bottom here, we're going to draw a point here. And by the time we reach here, we'll have reached our lowest point here. So we're just effectively tracking this 90 degrees behind it. So if I plot several points that are 90 degrees behind, then I should be able to just draw through those points. Here goes. Something like that. Question 2. Describe an investigation that will allow you to accurately determine the focal length of a converging lens using a graphical method. Okay, so we're talking accurately and we're talking by a graph. Labeled sketch of the apparatus, the measurements that you should be taking, a graph that you would draw using your results, how the graph is used to find an accurate value for the focal length of the lens. Okay, so a sketch of the diagram. So remember with the accurate version you want to take lots of U's and V's, so you have like an illuminated object and some kind of screen and your lens in between. So you've got your illuminated object. So you've got your converging lens, you've got your screen, and you move these until you get a sharp image, and then you're obviously going to need to have some kind of meter stick or something for measuring U and V. So something along these lines for your apparatus. So measurements to be taken, well obviously we're going to be measuring U and V. Just noticing I forgot to label the lens holder. So we're going to set values of U here, this object distance, and then position the screen until we get a sharp image and measure the image distance. Clarifying also that that's what we mean, measuring from the illuminated object to the lens. So we then adjust the screen position by moving it back and forward along here until we get a sharp image, and then we measure the image distance V from the lens to the screen. And then you want to say, well, we need to repeat that for several values of U. So what graph would you plot? Well, the standard graph for this is to plot 1 over V versus 1 over U. So that graph should yield a straight line with a negative gradient, and both of those intercepts should be an example of value for 1 over F. So you can get both of them and take the mean of those. Okay, so you find F from the two intercepts. They're both going to be equal to 1 over F, and then you average the two results for F to improve your answer. Question 3. Part A. Explain the difference between Doppler redshift and cosmological redshift of light from distant galaxies. Refer to the source and the observer in each case. Okay, so regular Doppler redshift is when the source is moving away from the observer. Now you can't have that the other way around, but yeah, just one description will be fine. So regular Doppler redshift is when the source is moving away from the observer. Cosmological redshift, however, is more the idea that the space between the source and the observer itself is expanding. So something that will draw the distinction between the one that's based on motion and the one that's based on the universe expanding. Part B then. The spectrum of light from a distant galaxy contains a spectral line of wavelength 398.6 nanometer. The same line when measured in the laboratory has a wavelength of 393.3 nanometer. Calculate the recession speed of the galaxy. Give your answer to 3 significant figures. Okay, so we've got a laboratory value and a moving galaxy value, And the moving galaxy value is obviously bigger because it's redshifted, and that's what happens to wavelengths when they redshift. So we're interested in finding the difference between those and putting it over the accepted value, which is the second one. And that will then equal the recession velocity of the galaxy as a fraction of the speed of light. And so we can get v, the recession velocity of the galaxy, by cross-multiplying the c. So now we just substitute into that. So just quickly calculate delta lambda up here, 398.6 minus 393.3. That's going to give us a value of 5.3 nanometers. And now we can sub this into our equation. Okay, so we've got 5.3 times the speed of light over 393.3. And we don't need to put those into nanometers, convert them to meters, because the delta lambda and the lambda are in the same units, and this is just a ratio. The only thing we need for them is that they're in the same unit as each other, and then the ratio will be the right value. So put that through the calculator. Okay, so to 3 significant figures, that's going to be like 4.04 times 10 to the 6 meters per second. Part 2 then, use Hubble's law to estimate the distance to this galaxy. So we have an equation for Hubble's law. V equals h naught d. So d is going to be v over h naught. And that's going to be our value from before, 4.04 times 10 to the 6. And the Hubble constant comes in from your formula sheet at 2.4 times 10 to the minus 18. And so we just bump that through the calculator. And I'm getting that. And since our value for h naught only goes to 2 significant figures, then we need to quote only to 2 significant figures because we're being limited by the 2.4. So that would go down as 1.7 times 10 to the 24 meters. Why is this considered to be an estimate of the distance? Well, the main reason is that h naught itself is only an estimate. It's based on various kinds of experiments that don't agree to a very high accuracy. It also assumes that the velocities are constant as well, which they probably wouldn't be. But yeah, h naught itself as an estimate is a simple enough answer, and that's certainly what the mark scheme is suggesting you put down. Question 4. The wavelength of monochromatic laser light can be calculated using Young's double slit interference experiment. An arrangement for carrying out the experiment is shown in figure 4.1. The light emerging from a laser is coherent. Explain what is meant by coherent in this context. So it means that the waves belonging to the laser are travelling in phase. In one such experiment, the interference pattern of bright and dark fringes shown in figure 4.2 is observed on a screen that's 2.5 meters from the double slit. The separation of the slits is 0.27 millimeter. So you can see we've got fringes and gaps. So even though there are 6 fringes, there are only 5 gaps. So 5 fringe spacings equals 30.5 millimeters. So one fringe gap is going to be 30.5 divided by 5, which would be 6.1 millimeters. Part B, use the data to calculate the wavelength of the laser light. So we need to get together the things that we have found. We have an equation that lambda is AY over D. And so we need to think about what those values are. So D we were told is 2.50 meters. A we were told is 0.27 of a millimeter. And we should immediately write that in meters. And Y we found to be 6.1 millimeters. So we've got our projection distance, our gap between the slits, and our fringe spacing. And I suppose we should write Y in meters as well. And now when we substitute into that fraction, every number is in meters. And that makes sense because if we multiply meters by meters and then divide by meters, we should get an answer that it's in meters. But if any of these weren't, that would not happen. So let's substitute those numbers in. And I get that. And again, because we've got two significant figures in the numbers on the top line, we're limited really by two significant figures in our answer. So 6.6 times 10 to the 7 meters would be the way to quote that. Sorry, 10 to the minus 7 meters. Question 5, Part A. A person uses reading glasses in order to correct hypermetropia, long sight. Each lens has a power of +2 diopter. While wearing the glasses, the person's near point is 25 centimeters. Show that the focal length of each lens in the glasses is +50 centimeters. So we remember that power is 1 over the focal length when the focal length is in meters. So the focal length in meters will be 1 over the power, which is going to be 1 over +2. And that's going to be positive 0.5, which is also 50 centimeters. Part 2, when an object is placed at a distance of 25 centimeters from the glasses, describe the image produced. Okay, so this is a focal length of 50. We're putting the object at 25. So if you think about that, we are placing the object sort of halfway between F and the lens. And that is the position for what we call the magnifying glass diagram, the simple microscope. And if you'll excuse my awful drawing, this is sort of what we end up with. Sorry, I find it very hard to draw straight lines on this iPad. But yeah, it's a virtual upright enlarged, magnified if you want to call it, image. So remember, that all came out of recognizing that this was half of that and that therefore we were doing this. 50 is where F is, 25 is where we're placing the object. Okay then, part 3, complete the table 5.1 to show the range of vision with and without the glasses. Show any calculations in the space below. Now, for this first one without the glasses, we can sort of see in our diagram here that when we put an object halfway out, the image will form here. Now this triangle and this triangle are similar triangles. So if this is halfway and this is twice that distance, then we're going to be at F here. So the thing the person can see as a close object is actually 50 centimeters away, but the glasses allow them to bring the object to 25. Now obviously you can do that as a calculation also. But yeah, that would be a 50, but we can do the calculation for it. So if we say that we're using a focal length lens of 50, we're using an object distance of 25, that's what the glasses do, they allow them to have a close point, then the virtual image is their actual close point. So if we can find the V value, that's what belongs here. So 1 over V plus 1 over U equals 1 over F. So we fill in that. We don't know V, but 1 over u is 1 over 25, and 1 over f is 1 over 50. So we subtract 1 over 25 from both sides. 1 over 25 is like 2/50ths, so you're effectively subtracting 2/50ths from a 50th, leaving you minus 1/50th. And that means that v is minus 1 over 50, which means that, 1 over v is minus 1 over 50, so v is minus 50 centimetres. And that is what we had sort of surmised from our diagram here, that if we're here at 25, the virtual image will turn up at 50. So that's verifying what our diagram said. So that means that first value is 50. And now we can then apply the glasses and figure out where the far point is. So what we're asking in the second part is, if we've got the glasses on, what's the furthest away we can put an object? Okay, so remember, this person can see far away objects. Therefore, the virtual image that the lens creates will be at infinity. So you've got a v distance at infinity, a focal length of 50, and we're asking, where is the object? So those are our numbers for the second part. So we do the equation again, and subbing into that, we can sort of see that when we put v down as infinity, that element might as well not be there. So this 1 over infinity is nothing, so 1 over u becomes equal to 1 over f, so u becomes equal to f. And so the final answer is 50 centimetres. Part B, figure 5.2 shows a diverging lens with an object OA placed perpendicular to the principal axis. The points F and F' are the principal foci of the lens. On figure 5.2, draw suitable construction rays to locate the image of OA, label the image IB, and show a suitable position of the eye for viewing the image. So we've got 2 rays that we can construct. One that runs parallel to the axis and then diverges as it's coming from F. Remember, we have to do that because this is a diverging lens. That's why the arrows point inward in this symbol here. So the ray parallel will diverge, and a ray through the optical centre will continue on in a straight line. And so those are the 2 rays we want to draw. A parallel one that diverges as if coming from F, followed by one through the optical centre, which keeps going. So you send it up parallel to the axis until it hits here. And now you want to put your ruler in line with these 2 points so that you can diverge it as if it was coming from F. So runs parallel, then diverges as if it's coming from F, and then the other one runs through the optical centre and doesn't change direction. And that looks like that. So where these rays that are emerging here appear to meet is going to be a point back here where that ray, there's a common point that both of those emerging rays appear to come from. And so if we dot this one back, we should find the place where the image is located. And that is this location here. So that's where we draw our image. And we're meant to label that IB. And we're meant to put an eye on here to look at that, and so the eye would need to be in this sort of region to look at it. And that's us, I think. Question 6, Part A. Explain what is meant by the photoelectric effect. So remember, in the photoelectric effect, you have electromagnetic radiation striking a metal surface and little electrons being emitted from that surface that we call photoelectrons because of how they were produced. And the energy in the electromagnetic radiation, light usually, needs to be above a certain frequency for this to happen. And below the certain specific threshold frequency, nothing happens. They don't emit any photoelectrons. So something along those lines. When electromagnetic radiation above a specific frequency is incident on a metal surface, the metal starts to emit electrons, called photoelectrons. The photons must have energy greater than the work function of the metal. Part B then. A piece of zinc metal is represented in figure 6.1. It contains fixed ions and delocalized electrons as shown. The threshold frequency of zinc is 1.04 times 10 to the 15 Hertz. So the black dots are the delocalized electrons and the big circles are the ions. Calculate the work function of zinc, giving your answer in EV. Okay, so the threshold frequency is like the minimum photon that will emit photoelectrons from this. So it's equal to the energy of that photon equals the work function of the zinc. So we've got an F naught of 1.04 times 10 to the 15 Hertz, and phi, the work function, equals HF naught. So we can get H, the Planck constant, from your formula sheet. And so if we combine those, we should get an answer in joules, and then we can convert it to EV. So H times F naught would look like that. And if we put that through the calculator, we get 6.89 times 10 to the minus 19 joules. And then we divide by the elementary charge, 1.6 times 10 to the minus 19. Again, you can get that from your formula sheet. Divide by that to get it into EV. And that's going to be 4.31 electron volts to 3 significant figures. And this is a bit of a pet question with CCEA. Part 2, when a piece of zinc is illuminated by radiation of a single frequency, the emitted particles have a range of kinetic energies. Explain why this is the case. Okay, so you can imagine, if we look at their wee diagram, that, some electrons may interact with the photon right at the surface, and they get to leave with all of their kinetic energy. But some electrons may interact with the photon much deeper down, and they have to make their way to the surface, and that causes them to lose some of that kinetic energy as they leave. So this person here, this little electron, can leave with all of their kinetic energy, and this one may only leave with some of their kinetic energy. And so you get a range between the fastest ones that were emitted right at the surface and towards the outside, and other ones that are emitted, but they had to crawl their way to the surface and they've lost some energy in collisions on their way up. Okay, so there's a difference between those two because of that. So something explaining that. Okay, so I've said the amount of kinetic energy an electron leaves with depends on how close they were to the surface when the photon was absorbed. Deeper electrons will lose energy on the way to the surface. Question 7. A simplified energy level diagram for an atom of hydrogen is shown in figure 7.1. Part A. Explain why the energy levels have negative values. Okay, so this is all about the idea that for you to get one of these electrons out of the hydrogen, you would have to pay over some energy to get it to the surface. You imagine that when you bring an electron from the ground state, you have to pay energy to bring it to these higher states. So by the time it gets out of the atom with no energy, you will have had to have paid all of this amount to get it up to there. So technically, any energy you give it would have to have this amount taken off it to let you know how much kinetic it would have after it had left. And so yeah, there's an energy that has to be handed over to remove the electron, and so it counts as negative while the electron's still in the atom. So it's an awkward thing to explain, but yeah, energy must be supplied in order to get the electron to this position just out. So if it reaches this position and it's got zero kinetic energy, we had to supply all of this, so it counts as negative. You know, so if you gave it, say, 4 times 10 to the minus 8 joules, you would have to take this off it to figure out how much kinetic it leaves with. Part B then. An electron can move between energy levels within the atom if a photon of wavelength 652 nanometers is emitted. Between which energy levels has the electron moved? So what we do here is we figure out what the energy of this photon is using E equals HF or HC over lambda, since we've got a wavelength in this case, and then we figure out, are any of the gaps in this diagram that amount of joules? Okay, so figure out the energy here. We need to do an E equals HC over lambda, and so we can just sub into that. H, the Planck constant, and C, the speed of light, will come from your formula sheet, and lambda is the value they've just given us. Okay, so we've got our Planck's constant, our speed of light, and our 652 nanometers. Okay, and we fill that in to your calculator now. And I get that, which is 3.05 times 10 to the minus 19 joules. And now our job is just to look at those energy levels and see if any of those gaps are 3.05. So let's have a look. Any of these 3.05? Well, yes, it's going to look like that. Their gap is 3.05, isn't it? 2.40, 5, and 5.45. So this transition is going to be C and B. Okay, so we just check what they've asked. Photon is emitted means it's a transition down. Oh, I've just unhooked that, annoyingly. Okay, so transition down is going down the way, so C to B. And that's it. So remember, if it was an absorbed photon, it would be going in the opposite direction, so it would be B to C. But because it's an emitted photon, we're transitioning downward. Part 2. An electron in level A is struck by a photon of energy 1.75 times 10 to the minus 18 joules. Which transition might occur, if any, and why? So let's look at that energy level diagram again. So what we're basically asking here is this value 1.75 any of these transitions? Is the gap between any of these transitions exactly 1.75? And if you look at it here, if we are jumping from here, we want to know where we would get to by adding this amount of energy. So we want to know the difference between 2.18 and 1.75. And would adding that amount of energy leave us with one of those top numbers? And if you do that, you get 4.3 times 10 to the minus 19, which is somewhere between these two numbers, but not equal to either of them. So that's why there could be no transition, because there is no exact jump to a higher level that's exactly that size. Part C, electron transitions between energy levels are involved in the production of X-rays for medical imaging. This is a result, of high energy electrons striking a metal anode. What do the letters CT represent in CT scanning? Okay, so that's just straight out of your notes. Part 2, state 3 differences between CT scanning and conventional X-ray imaging. So there are several things. Firstly, an X-ray image is a 2D image, whereas a CT is a 3D image. You're going to get like a higher dose of X-rays getting a CT because it's like multiple images, where an X-ray is a single image. And other things like CT would be better at imaging, more soft structures that are different to like bone, that a regular X-ray would be good at imaging. And these are some options put forward by the mark scheme. So they mentioned CT uses a moving detector. So a rotating X-ray tube for a CT, whereas it'll be fixed in a regular X-ray machine. And you can see they've been relatively generous. They've given several differences and asked you for 3 of those. So the marker just has to find 3 of the things mentioned to get your marks. Question 8, Part A, calculate 1, the momentum, and 2, the velocity of an electron with a de Broglie wavelength of 3.17 times 10 to the minus 11 meters. So we've got a calculation for momentum, calculation for velocity. So we need our little equation for the de Broglie wavelength. So de Broglie wavelength lambda equals h, the Planck's constant, over p, the momentum. So p is going to be h over lambda. And you get your you get your Planck's constant from your formula sheet. So just filling that in then. And so that comes out to be 2.09 times 10 to the minus 23 kilogram meter per second. And then the momentum is the product of the mass and velocity. So velocity is going to be momentum divided by mass. And again, you can get the mass of an electron from your formula sheet. So subbing in, we get that. And put that through our calculator now. And I get that, which is like 2.29 times 10 to the 7. So need to move these so we can see that next question. B, diffraction is the name given to the spreading of waves after they pass through an opening. What is the condition under which maximum diffraction occurs? Okay, and that will occur when the opening width is equal to the wavelength. C, in an experiment to demonstrate electron diffraction, a narrow beam of electrons is directed at a thin metal foil. Part 1, the beam of the electrons is produced by an electron gun where a high voltage is applied between a cathode and an anode in order to accelerate the electrons. Describe and explain the effect on the diffraction pattern when the accelerating voltage is increased. So again, if you accelerate them more, they will have a higher momentum. So we can think in terms of what will happen to their de Broglie wavelength. So if you increase p, then because lambda is h over p, increasing p will reduce lambda. So that's going to give you a smaller lambda compared to the gaps. So the gaps are much bigger now than the lambda, so you're going to get less diffraction. So the pattern will actually get smaller. There'll be less diffraction. Part 2. In this demonstration, the thin foil acts as a diffraction grating. What is the effective number of lines per millimetre if the second order diffraction occurs at an angle of 40 degrees? The de Broglie wavelength of the electrons is 3.17 times 10 to the minus 11. Okay, so we've got an n equal to 2, a lambda equal to 3.17 times 10 to the minus 11 metres, and a theta of 40 degrees. And we've got an equation that says d sine theta equals n lambda. So d would be n lambda over sine theta. So putting that through the calculator then. So we get a d of 9.86 times 10 to the minus 11 metres. And to get the lines per millimetre, we just would see how many times that would go into a millimetre. So 1 millimetre divided by d will tell us how many d's fit into a millimetre. And that comes to that figure, which we can write down as 1.0 times 10 to the 7. Question 9. Part A. State Snell's law of refraction. Okay, so this is the old sine I over sine R thing. So when we state that in words, we say, for light going from one material to another, the ratio of sine I to sine R is a constant. Something along those lines. Part B. In an experiment to verify Snell's law, the path of a ray of light was traced as it passed from air through a rectangular glass block and out into the air again. This is shown at figure 9.1. Use the angles given to show that the refractive index of the glass is 1.51. So if this is a parallel-sided glass block, then this here is going to be 60 degrees. And this here is going to be 35 degrees. So we can take this as our angle of incidence here. And this is our angle of refraction here. And so we can do sine I over sine R and get a refractive index. And so that's going to be like sine 60 over sine 35. And that comes out to be 1.51. Part C. A ray of monochromatic light passing through a section of an optical fibre is shown in figure 9.2. The ray travels from air into the core material with an incident angle A. The core material is glass of refractive index 1.51 and the cladding material surrounding the core is of refractive index 1.45. The ray is incident on the core cladding boundary at the critical angle for this pair of materials. What is the speed of light in the core material? So we need to figure out the critical angle and then work back from that. So we have the refractive index of the core glass. So we can say that the n from air to glass is equal to the velocity in air over the velocity in glass. And consequently then the velocity in glass will be v in air over the n for the material. And that's going to just be the speed of light over the n of 1.51. And that comes out to be 1.99 times 10 to the 8 meters per second. Part 2 then. What is the refractive index for light travelling from the core to the cladding? Okay, so again, the n for the interaction is going to relate to the n's for air to core and air to cladding. It is possible to create a combination of those that will give you the n from the core to the cladding. So if I start off with thinking about the n from the core to the cladding, I can construct that from an N for the core to air, followed by an N from the air to the cladding. So it's possible to show that if these terms in the middle are the same, then you can combine these into an N from this thing to the thing you end up with. Now, N for air to the cladding is the number we've already got. N for core to air is going to be the same as 1 over the N from air to the core. So that's our next line, is to rewrite this as N, 1 over N from the air to the core times that other N. And so if you put 1 over 1.51 and multiply that by 1.45, which is the air to cladding value, you get 0.96. Okay, now this may initially look like some kind of like magic trick, but remember that the N from the core to air can be written as a ratio of velocities of light, and the N from air to the cladding can be written as a ratio of velocities of light. So if you take the product of these, you'll be starting here, the A's will cancel, and you'll end up here. So it is easy to demonstrate that this works, as long as the things either side of the multiplying sign are the same material. You can start by going in here and come out here, and you'll end up with the same refractive index. And the only other thing we did was to use a number here that we knew. So to write this, we would write 1 over the N going in the opposite direction. So if we want N for core to air, we write 1 over the air to core value. And so the product of these gives us this, which gives us 0.96. And that makes sense, because when we go core to cladding, we should be heading towards a less dense material. Question 10. The speed of sound was measured using a resonance tube arrangement as shown in figure 10.1. A loudspeaker was placed above the open end of a tube. The length of the tube is 75 centimeters. The signal frequency was then raised from 0 Hz until an exceptionally loud sound was heard for the first time. Okay, so you're starting at 0 Hz, and eventually you're going to hit the fundamental. This frequency is called the fundamental frequency F0. And so that's our setup there. And then it says, resonance is the effect which results in an exceptionally loud sound being heard. Explain why resonance occurs. Remember, resonance is when the frequency being produced by this equals the natural frequency of this tube. Okay, so when it hits one of the natural frequencies of this tube, in our case the very first one, the fundamental, we get an exceptional amount of vibrations occurring here, because it's a special matching of this frequency to the natural frequency of this tube. Okay, something that basically talks about the frequency of the speaker, the driving system, and the frequency of the resonance box, in this case the tube and the column of air contained within it. So it's when they match up that you get the strongest signal. Part B, the method described will identify the position of resonance, or the first position of resonance. On figure 10.1, label the position of a node with the letter N and a position of an antinode with the letter A for the first position of resonance. Okay, so I'm just going to add in a tube diagram so that I can do that. So the first position of resonance, we'll start with a node here and reach an antinode up there. Okay, so you've got a node down here and an antinode up there. Describe how the air particles in the resonance tube are behaving at N and A. So at the node, you've got effectively 0 vibration, and at the antinode you've got like maximum vibration. So something along those lines. Part 3 then. The fundamental frequency F0 is 114 Hz, and when the first position of resonance is identified, use this information to calculate the speed of sound in air. Okay, so we know the details of that tube, and we know this frequency. Now, if I go back to this diagram, the tube contains, at the fundamental, a quarter of lambda, and the previous diagram told us that the length of that tube was 75 centimeters. So we have lambda over 4 equals 75 centimeters, and we have F0 equals 114 Hertz. And so if we multiply lambda, or multiply 75 by 4, we get the actual value of lambda, which turns out to be 3 meters. But we also have F0 here, and so we can use V equals F lambda to find the speed of sound. So 114 times the 3 meters. And so we get 342 meters per second. Okay, so part 4 then. The frequency is increased from 1 and 4 until the next position of resonance is identified. Calculate the frequency at which this will occur. So if we think about our tube, we need to get a node at the bottom and an antinode at the top. So the next way of doing that is for the wave to cross over. Let me see if I can show you that. So we start in the middle, we go all the way out and back to here. Start in the middle, we go all the way out and back to there. Sorry, that's terrible. Go all the way out and back to there. So you can see that that's actually 3/4 of a wavelength, and it's still the same length of tube. So that's now how we calculate lambda. So lambda will equal 4 times 75 over 3. So that gives us a lambda of 1 meter. So F equals V over lambda, and that's going to be 342 over 1, which is going to be 342 Hertz. And that's it. Thanks for watching. See you later.